We have this concept of interval of convergence and radius of convergence. And the bottom line is that as it turns out, the set of x for which that series makes sense always form an interval whose center is x, exactly that 8. And therefore you have this concept of the half-width of that interval, which is called the radius of convergence. And last time I mentioned very briefly why it is called radius convergence. There is actually a much richer theory behind it, which is very powerful. And then that's 10.8, and in 10.9 we talk about, okay, now you have a power series, and then it has the interval of convergence, and if you are within that interval, then you can carry out that infinite sum, and then it sums to something. And that something depends upon the value you are at, the x value. And therefore that sum becomes a function of x. And so you have this notion that a series sums to a function, a power series sums to a function. And so you ask what kind of function can arise from that, right? So in that section, we primarily focus on a class of functions that one way or another has to do with this function. And this one in turn is closely related to geometric series, right? And then the key is that in order to go from here to elsewhere to other functions related to it, the key fact is a big theorem, which essentially says that in many ways, power series behave very well. If you have a power series within the interval convergence, there's some very nice function called analytic function. Analytic function is more than just function which can be differentiated infinitely many times. It's far more than that. Or can be taken on that derivative infinitely many times. So it's more than that. It's the function that can be represented by power series locally. Right? So that means that guy is an analytic function because it's representable by a power series. Right? And then the good news is that if you have a power series that converges within the interval of convergence to a function f of x, and this f of x is extremely well behaved. It's an analytic function. Among other things, you can differentiate, you can integrate, and as you do so, the series side, the right-hand side, it behaves naturally. You can integrate turn by turn, you can differentiate turn by turn, the way that you would expect of polynomial. It's as if it is infinite many terms polynomial. That's simple. And therefore, from this, if you take the derivative, the next guy, 1 minus x squared, that's the derivative of this guy, then it also has power series expansion around x equal to 0. You just take that power series of this guy around 0, and you just turn by turn differentiate, and then get